Have you ever looked at a furnace schematic and felt the sheer weight of the energy we are trying to contain? So, we are just moving metal. We are managing a high pressure environment that is constantly looking for a way out. On the screen, you see the complexity of our system from the gas scrubbers to the tap hole. It's easy to get lost in the blueprint, but every line on this chart was refined by an accident somewhere else. Think of the blast furnace like a high pressure boiler that also a chemical reactor. If the balance shift, the physics takes over. This is not just theory, it's a diagnostic breakdown of historical failures and absolute protocol we need to survive them. So, what happens when those protocols are ignored? To answer that, we have to look at the monument that no steel workers ever want to build of them. What does a total structural failure actually look like? On March 12, 1990, at Steel number 1, a 1513 cubic meter furnace didn't just leak, it disappeared in a ball of fire and smoke. This image of the center of the 19 operator killed that day. The explosion was so violent that the part of the furnace shell were thrown over 200 meters away. So it was not a glitch, it was a catastrophic collapse of the supporting structure. So, what here is sobering? When we ignore the warning sign, we are not just risking a shutdown, we are risking the complete erasure of the facility. But how do we get to that point? It starts with understanding that explosion are not act of God. So, do you believe in bad luck in the casting house or cast house? We can say, I don't. Every historical explosion is governed by three predictable physical and chemical mechanism, as it is shown in the slide. So, look at these three pillars. We have gas air ignition. This is basically a threat from the combustion, water gas knocking, the chemical threat, and the phase changes expansion, the physical threat. Think of these as the three way a balloon can pop. You either overfill it, the material degrade, or you cause a reaction inside that the skin cannot hold. So if we can identify these all types, we can prevent them. So let's dive into most common one, the combustion threat, and which are very prone. So, why is the blast furnace usually safe from the internal combustion? It's the operational paradox. Because internal pressure is heavily positive, air supply cannot get in. For an explosion, you need this combustion triangle gas concentration between 35% and 75%, oxygen introduced into the system, and ignition source like a 700 degree centigrade spark. So it's like a pilot light as long as pressure is pushing out. The flame stay where it belongs. So the danger only arrives when we reserve that pressure gradient. So how does a sealed positive pressure system suddenly start inhaling outside air? So have you ever seen a breeze form in the shaft? So it's a nightmare scenario. In a normal descent, the body moves down smoothly, as it is shown in the figure. But if you get cooling leaks or thermal irregularities, you get breezing. a crust of material hanging in the shaft with an empty void beneath it. So when that breeze finally collapses, it's like pulling a piston back in a syringe. It creates a massive momentary internal vacuum that sucks ambient air inward through shell crack or open valves. Now we have just hand delivered the oxygen to fuel. This is exactly what happens during the geosteel autopsy. So was geosteel a surprise? Not if you look at the maintenance log. It was a domino effect. First relining was relieved. 75% of the cooling plate were already destroyed. To compensate, they sprayed high pressure water on the exterior cell, which caused 28.5 meter of thermal fatigue crack. Then two air failed, dumping water inside and creating dull zones. Finally, they had a massive slip. The vacuum triggered, and the shell, already weakened by crack, could not hold the ignition. The source what is that they tried to negotiate with the physics to keep production up, and physics said no. But the furnace stack is not the only place where gas can pool. Who here keeps a close eye on the dust catcher? History says we should. We have seen explosion in the downcomer pipe because a flame was extinguished for 3 hours, allowing gas to pool. We have seen explosion between the belts because an equalizer valve closed too late, sucking in air that hit 600 degrees centigrade center. Even hot blast stoves are not safe if a shut-off valve fails. These are not uh, mm, stack failures, they are system wide vulnerabilities. So, to stop these, we have to move from best practices to absolute mandate. And uh, then naturally, question arises that what are our lines in the sand? So, there are four. First, absolute separation, zero tolerance for gas and air mixing in pipes. Second is the 500 PA rules. If pressure drop below 500 Pascal, you must instantly introduce steam to displace oxygen. Third, continuous purging of dead spaces like bellhoppers. And fourth, maintenance integrity. You cannot bypass relining schedules when your cooling systems are failing. These are not just suggestions, they are survival requirements. Now let's look at different best. When the chemistry of the gas itself changes, what happens when we pump water onto red hot coke? We are not just cooling it, we are creating a fuel factory. This is the water gas reaction. Carbon plus H2O gives you carbon monoxide and hydrogen. If that hydrogen concentration in the top gas hit a critical threshold of 4 to 5%, knocking an internal chemical detonation becomes inevitable. It's like turning your furnace into a giant hydrogen bomb. The key to stopping this is how we apply the water. So, look at the difference a few years of tech can make. The orange line is March 1984. They used heavy unbroken stream of water that went deep into coke bed, spiking hydrogen to a lethal 9%. Now look at the blue line from 1987. By using atomizing spray, a fine mist, they achieved cooling without deep penetration. The hydrogen stayed safely below 2%. The so what here? Technology like atomization is the difference between a controlled blow off and a demolition. Finally, we have to talk about the fastest explosion of them all, the phase change bomb, which is more dangerous, water on metal or metal on water. It's always the latter. Water on metal is just steam escaping the enemy. Energy dissipates. This energy dissipates supposed to be very important. But metal on water, that's encapsulation. Water expands 1600 times its volume instantly when it flashes to steam. If that steam is sealed under a layer of liquid iron, it has no escape vector. The containment vessel, whether it's a runner or a ladle, will shatter like glass. We saw the lethal reality of this at Victoria BF. How does the 2 cubic meter of water kills 11 person? Through a series of a small oversight, a broken two-air cap flooded a hot metal runner and the water pooled secretly at the bottom of a torpedo car. When the 1400 degrees centigrade metal was poured in, it sat on top of that pool, the trigger. Moving the car, the rocking motion caused the metal to fold over the water, encapsulating it. The resulting explosion blew a 1.25-ton nozzle 21 meters into the air and rained 80 tons of molten iron down on the crew. So let's summarize this threat so we can carry them back to the floor. So if you remember nothing else today, remember these matrix. We have our three categories: combustion, keep the pressure up; chemical, control the hydrogen; and physical, keep it dry. This is your cheat sheet for risk assessment. If you see a vacuum drawing air in, you are in the first row. If you see hydrogen spiking during a blowout, you are in the second. If there is a standing water in the casting house, you are in the third. Why do we keep seeing this pattern repeat? It usually comes down to one fatal trade-off. We all feel pressure to meet quotas right. But look at this scale. On one side is yield, on other side is physics. At Zeo Steel, they use high pressure water to keep a damage cell running just to hit production numbers. Every major disaster in our history shares this permeable, pushing damaged systems past their absolute physical limits to maintain a schedule. You can negotiate with your manager about production, you cannot negotiate with thermodynamics. I will leave you with one final thought. These disasters were not anomalies, they were predictable reactions to operational compromises. Our discipline is the only thing standing between a productive shift and a centograph event. So, honor the history, protect the future. Let's make sure the lesson written in blood remain the laws of our floor.